Hello, my name is Michael Salome. I'm lead data scientist at Cambridge, Salesforce. And my talk is about visual search. So I think I will need this cue. Excellent. So we're searching all the time for our missing keys, for new drug compounds, for black holes. This is what you're watching here is a zoom through to the supermassive black hole at the heart of the elliptic galaxy, Messier 87, enhanced by a binary neural network for super resolution. On the left, you see a Hubble deep field, and on the right, you see a few million integers. It's a UMAP projection of sparse vectors for about 1 billion numbers. And whether you're searching for black holes in astrophysics or counterexamples to mathematical conjectures, deep learning is really the only game in town, especially for content-based search. We like to say that deep learning is neurologically inspired, and to see basically the scale of how hard visual search can be, consider that the number of synapses in your brain, the 200 trillion, is dwarfed by just the number of 100 pixel thumbnails, or 10 by 10 by 2 tensors. So image space is very, very large. But that's okay. We can model very complex subspaces. This is an experiment I did a few weekends ago. On the left, you see, again, training to generate iterated function systems. And on the right, you can see the output. So basically, we're interpolating smoothly over some random coordinates and the resulting parameterization. That's fun, but rather abstract. So more to the point, can we model the distribution of all man-made products? Here, you'll see the image space we've sampled of all images of handbags. And this is what it would look like if you could do that. And in essence, that's what we've done. So here's a quick demo of what we've built. This is one of our early adopter clients, Rebecca Taylor. We have a demo of our visual search API running on a mobile browser. So it allows shoppers to act on moments of inspiration and to, just with their camera, search for new dresses, as an example. So I mean, there's only about 1 billion visual searches each month that we service, which is about 100 times less than the number of text searches. But as a reference point, the image recognition market, it's estimated to grow to around $40 billion this year. So, you know, visual search is still a very hot topic. So for the remainder of the talk, I'm going to be first covering the basics of what visual search is, the problem, and then I'll be touching on our solution, the various methods we've used, and hopefully offer some tips and useful advice, insights that we learned along the way. So the visual search problem. So formally, you're given some large predefined set of images, and what you have to provide a function that takes any query image and returns a ranking of similar looking results from a database. Sounds easy enough. At last, your function is evaluated by some metrics. We typically use average, normalized, modified retrieval rank, but you can use precision or recall or whatever you'd like. Visual similarity is it's a little tricky of a concept. It has different connotations, and two specific ones that you should keep in mind are perceptual and content. So in general, you want to establish a model that can understand both the low-level and the high-level notions of visual similarity. And there's always a trade-off between these two. So you can search along multiple dimensions of products. And in this example, one of those dimensions is color. And you have to decide, where are we going to surface, say if you search for a dress and that you find a handbag with the exact color of that dress, where in your rankings do you return it? These are really important questions that you need to be able to address. And so how do you do that? Well, learning semantic similarity involves just finding some function, which turns out to be a deep convnet, and it maps images into what we call the latent space. And the latent space looks like this after you've trained your network. It groups things that are similar together. And hopefully it looks like this after you're done training. But where do you get the data to train on? So this is always like the most important question, right? How do you get your training data? And for specific domain problems like fashion parsing, right, we can't just use off-the-shelf technology, off-the-shelf benchmarks. A lot of times in the real world, academic data sets have non-commerciality clauses. You're not allowed to scrape certain sources. It's a very legal, lots of legal issues. But you can get creative, and you can build. You can work with Amazon Turk, and you build human-in-the-loop systems to automatically train data and expand your corpuses. Or you can get creative, and this is one of my favorite examples of data set construction. So to make a retrieval data set for locations, you can use the Google Maps search time machine and find images of the same locations in geographic space at the same time, at different times. And that was a really cool way of making a data set. This is what it would look like if we had perfect labels for this problem. And it involves the mixture of in situ labels, or in the wild labels, where images basically looking like social media content, or what we call iconic images, which are these beauty shots of the catalog images. And you need to have a mapping between them. And that's very, very expensive and hard to get. So what we ended up doing was synthesizing a lot of the data. So you can use pose estimation in conjunction with things like depth reconstruction models and synthesize a much bigger training data sets. Basically, that allows your networks to understand that they need to ignore different backgrounds and understand the various contexts in which certain products appear. Let's see how I'm doing for time. Okay. We have a lot of weak labels. We've got to make use of text. That's always a really good idea. For retrieval benchmarks, on the left you see a t-SNE projection into 3-space of fashion MNIST. And on the right is basically LeNet trained to separate the classes into 2-space. And this is a very shallow network trained on about a few seconds of CPU time. So it's a super easy benchmark, but I want to call it out because everyone uses MNIST, and it's too simple. Fashion MNIST is much harder and it's basically a drop-in replacement for MNIST. And unfortunately, most retrieval data sets in the literature are based on things like architecture, Stanford, Oxford, Paris, all those data sets. But you can certainly validate with deep fashion. Deep fashion is one of the training data sets. You're not allowed to train with it, but you can validate with it. So what does the solution look like? Well, you can take off-the-shelf CNNs and do transfer learning. That was the state of the art. A few years ago, maybe 2016, you'd use RMAC or bags of visual words with a fine-tuned network. And this only gets you so far. If you use these techniques, you end up with these sorts of situations where your chairs, okay, you've used a classification network, so you're going to get chairs back, but they won't be attuned to certain visual features or stylistic features that you want them to be. So the more modern deep learning solution, and the one we decided to use, was a Siamese network. So this uses shared weights. And it learns a mapping, a function that maps between inputs such that the L2 norm right? And the target space approximates the distance between the input, the examples in semantic space. And right, the common way of doing this is with triplet loss. This minimizes the distance between query and positive and maximizes the distance between query and negative samples. There are a lot of losses you can use, and you can get lost in the losses. But the key idea to remember is that you're minimizing intra-cluster distances and maximizing inter-cluster distances in the training samples in your mini batches. And you can derive loss functions that can do this very efficiently. And that's sort of the key idea. For architecture, we used a variant of RetinaNet, and this is a great topology for detection. It's a little bit more accurate than SSD and mask RCNN, a little bit slower, but you can speed it up. For retrieval features, let me go back. For retrieval features, we used custom variants of ResNet, and we optimized them with the little neural architecture search, ENAS and darts. So that's half of the story. Once you have the net, the rest is engineering, but it's non-trivial. You have a network. It produces a feature embedding, okay, which is a vector for a given image. But unfortunately, this is not very an efficient thing to search through, right? So nearest neighbors is a very hard problem in general. It's too expensive. And so to accelerate it, you have to use approximate nearest neighbors. And we have developed a variant of approximate nearest neighbors algorithm that uses Hamming LSH and multiple vantage point trees to go beyond the state-of-the-art benchmarks, which are basically NMSlib. And this is a really elegant algorithm, LSH, and I wanted to explain it, but I have 15 minutes, so I'm not going to be able to explain the approximate nearest neighbors. I wanted to get to the good part, which is sort of the learnings, the findings from going through this process of building this real-world API. So what are the tips? Well, if you're going to try to build your own visual search API, what you need to do is one thing is query expansion. We found this to be very, very useful. And that is, if your initial rankings are good, it's a very simple thing you can do. You take the descriptors of the top n results, you average them, and you requery. And this can really give a boost to your performance. Another thing that helps is to use something called diffusion on graphs. This is a new technique, and it basically involves building a network, a graph of your images, and then back-propagating relevance labels into your graph. Uses a pairwise affinity matrix. And we found that when you have detections and there's some bad results, you can filter based on entropy. And it's a really nice heuristic to clean up your rankings. And although we used architecture search, I found that it was basically not as, it was equally performant to something like hyperband or random search. So limited benefits there. The other crucial thing to do if you're building visual search is to have a golden set of images, set Y, and then some large corpus, and to as you iterate through new versions of your similarity search model, to run this test to see what the top, say, 30 or 50 nearest neighbors in X for each one in Y. And you can time it, and then you can qualitatively evaluate it. So this is what you do. If you had two separate versions of your models, you would run this test, and you'd see, okay, which is performing better qualitatively, and you can Turk this out. And it serves as a really, really helpful check to essentially qualitatively do a regression test on new versions of your similarity search models. There's another one. So yeah, very helpful to do this. And in parallel, you want to have two endpoints of each of your APIs that you can query as you increment or you make changes running side by side. So you can, in the process of doing the regression test, you can see what happens when you're changing or adding features to the API. It's very important. That was a big tip, something that really helps us. So I wanted to summarize and then give one last application of the Visual Search API. It's really just one component of what we call the Visual Intelligence Platform. And it's going to be one of many APIs we're going to be exposing to customers. And the applications are manifold. It solves basically the cold start problem for new products. You can create object-to-scene mappings. You can do outfit proposals, what we call completing the look. There's so many applications. Really, it enriches all of your data in your catalogs to have attribute APIs and visual APIs. So the last example I wanted to show is an example. It's really a byproduct of how we trained our retrieval net. So during training, we would force a certain sub-network or hypercolumn in the network to pay attention to the colors of the products, in effect computing a color dominance function from the product pixels. Once you have that information, you can index it, and then you can search by, say, a color slider. And this is what it looks like. So you can search by single colors or multiple colors palettes. And all of this was computed basically in a sub-column of our retrieval network, which is pretty cool. We didn't have to compute, say, color histograms. So it's just one of many applications that we have in store as we roll out the product. But I basically just wanted to say, check out Einstein.ai to follow along with our latest research at Salesforce. And feel free to talk to me or email me for other questions or information that you may want. So thank you very much.